Next up, Matias, which will be our final talk of the evening. So I'll hand it over. Good luck, mate.
Thank you. Those were some impressive presentations, so really good stuff. All right, so I am going to be talking about event-driven microservices, which seems to be the theme today. My name is Matias Salerno. I'm from Argentina, so if you like football, you know why I'm really happy. And yeah, I'm talking about microservices, so I'm going to be... Should I use this one? Let's see if it works. Oh, it does. Nice. All right. So, all right. Event-driven microservices. As I was telling you, I'm Mati. Everybody calls me Mati. I'm a subject matter expert at Globant on scalable platforms. I've been working with Globant for 10 years. I'm a software engineer since 2010, so it's been like 13 years almost. So yeah, it's been a while. So I work for Globant. It's a worldwide company. It was originally funded in Argentina. Now it's worldwide, has 25 countries, 27,000 Globers. So it's a big company. And yeah, as I told you, I've been working with them for almost 10 years, and I'm a subject matter expert on a scalable platform. So basically, any platforms that need to be scale, I'm the guy. And I'm also the host of a YouTube channel called Programming with Mati, where I'm also teaching about all this stuff about microservices and scalable platforms, event-driven, data streaming. So I haven't done anything on microservices yet, so this might be the first material. So you're getting the very first part of this. But I've been doing a lot of things on Kafka streams, KSQL DB, and functional programming, which is something that I really like. So if you want to follow me there, please subscribe. Yeah. All right. So how does the average microservices communication look like? Here's a small example, but sometimes we build microservices and then we start connecting them with each other, and we end up with something that looks like this. Services that do REST calls to each other and more like this. Because we don't really know what's going on. So we don't really know what's going on in there. We know that there are services and we know that they speak to each other, but we don't really know what is the flow. We don't know exactly how we got into that place. But here's sometimes how we get there. We usually start with a monolith, which is like we create a company, or there's a company that needs a software, so we create a software for that company, and that software starts to grow and grow and grow and grow and grow. And eventually we get tired of maintaining that monolith. So what do we do? We create microservices. Sometimes we tear the monolith apart, sometimes we don't tear it apart, we keep it there and we take care of it and we treat it as a baby. And then we also have all these other microservices around it. And we start connecting all the services with each other. And then we have the microservices entanglement, which is what we just saw. And another thing that I wanted to tell you, this talk that I'm doing now, it's been inspired by two projects I've been on. In one of the projects, I used a traditional microservice architecture where we didn't have event-driven architecture. We didn't have events. We didn't have an event bus. So, and then I worked in a different project in which we did. So we implemented that. So I started to notice things about the microservice architecture that didn't have events. And one of the things I noticed was that I couldn't easily understand the dependencies and the flow of the services. Like if you see the diagram that I showed before, let's see here, you don't really see a logical flow of it. It's like you don't know where the data is originating and where it goes and which services depend on which. You can start looking at some dependencies there, but it's really hard to understand. Then it's also sometimes those calls, those microservices calls, are synchronous calls, which make everything take a lot of time. Like if you are keeping a user on the back of the first call, then the user is waiting for 3 or 4 downstream REST calls, which is just absurd. And then managing distributed transactions in that kind of services, it's really hard. I've been working in the last 4 years with financial fintechs and financial institutions, so transactions are really important. Like things can't go wrong there. And so when you have microservices and you have a transaction that goes across multiple services which have different databases, and some part of the transaction went wrong, you really need to figure out how you will solve that, because it's not like a relational database where you can basically roll back and the transaction is gone and you can then try again. In this case, let's say I did a change in microservice in the database of the microservice 1, then I move on to microservice 2 and I fail. I need to figure out a way to roll back the first change without failing. So it becomes really, really hard to do. And also, managing upgrades on microservices becomes a full-time job. It's really, you have to keep track of different versions that you use of the microservice. And then all the microservices that are consuming that microservice need to also keep track of that version. So if I change an endpoint of one of my services, a slight change, I need to figure out how to tell the other guys, or I need to start creating new versions of the endpoints, and then I'll end up with version 10 of the same endpoint, but because I have new services that are using it and they need more data, then I'll have 100 versions of the same. So these are things that you start noticing when you're working with microservices. And this is the part where we say that microservices, even though they are great in a lot of things, complexity increases, and you really need to figure out how you will manage that. And sometimes you even have to figure out if it is really worth it, because there are some companies that would go from scratch to microservices, and sometimes it's not worth it. Sometimes you just start with a monolith, and if it goes well, then invest in a microservice infrastructure. So how do we improve the communication between microservices? All right. That's where we introduce the event-driven microservices. It's a way of modeling your microservice architecture where the unit of data is an event, right? The minimal unit of data is an event. And these events are produced by the services, and the services also react to these events. So we've seen in the example by Uplearn how everything was basically a reaction of events. So everything was triggered by events, and then some service reacted to that event and did something, and that produced another event that then it triggers another thing. So this is how event-driven microservices work. So Kafka is a distributed system. So basically, There we go. So this is how an event-driven microservice architecture would look like. These are the same services that we had before, but now everything is connected through a distributed message broker. This is one way to do it. There are other ways. But this is one way, and this is the way I did it. And in my case, the distributed message broker was Apache Kafka. I've been using Apache Kafka for 4 years now, and it's an amazing tool. It has a lot of different features, and it's really powerful. Like because it's not just a message broker; it's also distributed, and it's extremely reliable. So you can scale it. You can also have a lot of different copies of the data, so that in your cluster, data is replicated, and if some of the instances of Kafka go down, then you have replicated information somewhere, so where you can, and you can even connect clusters across different regions of the cloud. For example, if you're using AWS and you have different regions, you can connect this data in different regions of the cloud. You can connect the clusters and create like a multi-cluster architecture in which, if for some reason the whole US region goes down, you still have your UK cluster or your Asian cluster, and you can still function. That was one of the things that actually happened a few years ago. And Netflix was able to not stop working because they had multi-region clusters. So what is the idea here? The idea is that services are not talking to each other directly anymore. They're talking to each other through events, and these events are sent into the message broker, where we have all the different topics we call, where the data is stored. So the distributed message broker becomes a very important part of your architecture. It's the main source of truth. And everything that happens in there, you need to take care of it. Like the maintenance of that component becomes really important. But anyway, if you have these services talking to each other through events, now the services are not depending on each other. They are basically they're now less coupled to each other. Now they are coupled to data and not to services, right? Because they don't know about the other services. They just know about the data that they receive and the data that they produce. So if one service goes down, but I can still produce the same data, this service doesn't care. It's just they are depending on data, and they're depending on, and what do we mean? Is it completely decoupled? No, because this data has a format, has a schema, and that schema has to be somewhere. So there are tools that we use to keep control of that schema. And the good thing about this is that we can centralize this. We centralize it where the data is. We centralize the schema management with tools like a schema registry, for example. So that is a good thing about this kind of architecture. And we can model reality as it is. Like this guy said, Heraclitus, no man ever steps in the same river twice, for it is not the same river and it's not the same man. So basically, reality is a stream of events that are immutable. And that is the good thing about the message broker. You can model reality more closely to what it actually is, a stream of immutable events. So, as I told you before, the services are not aware of each other. They know the topics that they need to get information, and they know the topic where they need to produce the information, but that's it. And so what are the advantages of this kind of architectures? Services are not coupled to each other, but data. Then the data that is produced by the services is widely available for other services, including new services. So we know the data is there in the message broker, so we can consume it, and we can create new services, we can create new features, we can create new analytics, anything from that data that is in the message broker. Asynchronous processing becomes more easy to do because basically everything is being processed asynchronously. Once you put some data in the message broker, everything is a chain reaction, basically. You will, all the services will start to react to the new data and will produce new data, and in turn, other services will consume that data, and it's all a chain reaction. And because everything is asynchronous and stateless, it becomes really easy to scale and descale automatically as we want. And so we talked about the distributed transactions problem that we had, and how do we handle distributed transactions in this kind of architecture? Well, we have two advantages from this architecture that we can use. One thing is the single consumer per key, and the other thing is the eventual consistency. I'm going to explain both of them. What do I mean by single consumer per key? Here we have a message broker and 3 instances of the same microservice, right? And they are consuming data and saving into a database. What we do with the single consumer approach is that we partition our data using a key, and every instance will always be assigned the same key. And this kind of architecture, we can guarantee that this happens. And if we do that, and if we make sure that we consume events on the same key for the same reader, we'll avoid what is called a race condition, right? Let's say we have a bank balance that we need to update, okay? And there are 2 processes that want to update the same bank balance. What happens if one increases or decreases and the other reads before that increase? You would have all the information, right? So there will be an error, and your customer will be really angry because they'll have less money than they should have in their bank account. So what do? You put a constraint and saying only this instance will be able to write into this customer balance and none other. So with that simple solution, you avoid these race conditions. Since you have thousands of customers, you can basically split the amounts of customers between all the services. That's it. And then we have eventual consistency. And why do we talk about eventual consistency? We have a distributed architecture now. We have microservices. And microservices, they have their own databases, they have their own, we can call them materialized views, right? So these are views of the data that have been materialized and saved. So for example, if I have a report of my expenses on a month, and that report is saved somehow that is a materialized view of the data. So if I have multiple materialized views of data that relies on the very same events, if I have a materialized view of the data that relies on the same events, then what happens? This data sometimes might be inconsistent because they rely on the same events, but they might have not been processed. The event may have not been processed by the one of the microservices. So maybe it happened to you like when you are browsing in Instagram or any page, and you see that a particular post has an amount of likes, and then you enter to that post and you see a different amount, and you see why? Because it's not yet consistent, but it eventually will. And this is what eventual consistency is. It's a characteristic of an event-driven architecture in which all the views created of the data are consistent with each other once all the events have been processed by all the aggregation functions. All right? So what we want to aim here is we want to have a system that will eventually be consistent. And why do we do this? Because we cannot have a fully consistent system all the time, because we have multiple microservices, and each microservices has multiple databases, and it's all a big cluster of things. So because we want to scale, we have to, there is a trade-off that we need to do, and this is the trade-off. So what we say when we do this kind of architecture is you have to embrace this. You have to embrace eventual consistency. And what are the doors that are opened when we do these kind of architectures? Migrations from monolith into services become really easy. You can stream data from a database, from the database of the monolith into your message broker. And once you have the data there, you can create all the services and aggregations that you want. Serverless architecture becomes really easy to work with. So when you have events, you can basically do a serverless architecture. Serverless architecture is based on events, as we saw in the last presentation. It promotes functional programming, which is a great style of programming. I don't have to tell you, but it's one of the best ways you can approach coding is by doing small pieces of functions. And I have a whole series on functional programming on my YouTube channel. So if you want to learn more about that, you can look at that. And creation of new features becomes easy. Centralized data management and tools with tools like schema registry. So is this architecture, are events a silver bullet? No. It's not. I mean, still, you need to handle things that can go wrong, like we saw there in the AppLearn example, where you have to have dead letter queues, and there are a lot of different approaches for this kind of problems. Dead letter queues are the way to at least know about the issues. Like when there is an issue, you put the event that caused the problem into a dead letter queue, and then you handle it. You can handle it manually, or you can handle it with compensating events, which could lead to another problem. So there's no silver bullet here. Then there is data format that may change over time. So less coupling on the services, but the data, they still couple on the data. And the only solutions for this are schema registries, where you can handle that schema, the format of the data in a centralized way. And then the message broker, since it's so important, it also becomes very important for you to maintain it properly, to do a good management, and sometimes this leads to getting a SaaS license with a provider of the message broker, for example, because it takes so much resources that you will end up basically getting a new them to manage it for you. And this is more material that you can read about these architectures. I would recommend you to get familiar with Apache Kafka and all the libraries around Apache Kafka. Read about patterns like CQRS and event sourcing. Read about functional programming, and read about serverless architectures. That's it.